कक्षा में स्वागत है। आज डॉक्टर सेद हम पैरेललिज्म की शक्ति को खोलेंगे। जॉबलिब और डास्क के साथ डॉक्टर सेद प्रोसेसेस और थ्रेडिंग को समझेंगे। बेहतर स्केलेबिलिटी के लिए लेक्चर में स्वागत है डॉक्टर सेद।
Welcome everyone to Deep Learning for Intrusion Detection. Today, we're diving into a crucial topic that underpins high-performance computing in this field: libraries for parallel and distributed tasks. Think of this as learning how to turn your single-person task into a super-efficient, multi-person team effort. We'll start by looking at the core building blocks that make this possible. Let's use an analogy to clearly define processes and threads. Imagine a whole factory. The process is the entire factory where all the work happens. A thread is a single worker on the factory floor. A factory process can have many workers, threads, all performing tasks simultaneously. The key difference is the task size. Threads handle smaller, quicker jobs, while processes are for the larger, heavyweight tasks. This concept is essential because the libraries we use decide whether to hire a single new worker, thread, or build a whole new factory, process, to speed things up. Meet Joblib, our task manager. Joblib is an incredibly useful Python library because it supports both multiprocessing, new factories, and multi-threading, new workers. It intelligently decides which one to use based on its backend. The default backends are loky, which prefers creating new processes for better isolation, and threading, which uses new threads within the same process. I like to think of Joblib as the traffic cop, directing parallel operations to the most efficient route. Notice the option for Dask. That's our hint that we can even scale this traffic cop to a network of computers. Scikit-learn, a popular ML library, integrates beautifully with Joblib. While Joblib support isn't for every Scikit-learn function, it's there for the computationally expensive ones, the ones that really benefit from a speed boost. Look at the list on the slide. Linear regression, logistic regression, random forest. These are the workhorse algorithms that take time. Joblib steps in to efficiently execute these tasks, making your machine learning workflow faster and smoother. It's about leveraging parallel power where it matters most. Here are two gold standard recommendations for optimizing your parallel ML work. First, in k-fold cross-validation, assign your cores to the resampling procedure, not the model training. This is like setting up all your test environments first, and then running the single model in each. Second, for hyperparameter tuning, trying out many settings, make the search multicore, but keep the individual model training single core. The final takeaway from testing is crucial. Use only physical cores for the best speedup. Hyper-threaded cores might seem like more power, but they often come with a slight performance penalty. Let's shift gears to model evaluation with the SVC validation curve. A validation curve is simply a model's report card. It shows how well your model performs as you change a key setting or hyperparameter. We're using the support vector classifier or SVC here. The nJobs setting, which we've just discussed, significantly impacts the time it takes to generate this report card. Understanding how to set nJobs is key to optimizing your SVC evaluation. This slide represents the crucial setup phase. Just like a good chef prepares all their ingredients before cooking, we need to prepare the environment before generating the SVC validation curve. This step ensures that all the libraries are correctly loaded, the data is pre-processed, and our parallel processing options are configured. A clean setup is fundamental for getting accurate and fast model performance results. Here's the first scenario. nJobs equals 1. What does this mean? It's the single core setting. We're explicitly telling the system, I only want one worker on this job. You'll notice this setting will likely result in the longest execution time, but it provides a baseline. We use it to measure exactly how much faster our parallel methods are. Now for the power-up. nJobs equals -1. This is the all hands on deck setting. It tells the system to use all available cores for the SVC validation curve analysis. This setting is designed to give you the absolute best execution time and maximum efficiency. Comparing the results of n jobs equals 1 and n jobs minus 1 is a powerful demonstration of the value of parallel computing. To show this isn't just an SVC trick, we apply the same all-hands-on-deck strategy to the k nearest neighbors, or KNN, validation curve. Again, n jobs equals -1, utilizes all cores to accelerate the validation process for the KNN model. This reinforces the idea that parallel processing is a versatile tool across different machine learning algorithms. Let's touch upon the famous bias-variance trade-off. Think of a dartboard. Bias is consistently missing the bullseye in the same spot. Your model is too simple. Variance is hitting all over the place. Your model is too complex and sensitive to the training data. This slide shows a scenario with a single OS process. The goal is always to find the perfect balance. A model that is complex enough to be accurate, low bias, but general enough not to overfit, low variance. Moving on to deep learning. We are now preparing the environment for a TensorFlow feed-forward neural network. This is our biggest task yet, so proper setup is vital. This slide is a checkpoint. Everything is initialized and ready to run our neural network for training and evaluation. Get ready to watch the network learn. An epoch is one complete pass through the entire training dataset. So running the network for 10 epochs means the model will see all the training data 10 times, giving it 10 opportunities to learn and refine its internal weights. This slide is where we assess the model's learning trajectory and performance over these multiple iterations. If Joblib is a traffic cop, Dask is the orchestra conductor for parallel Python. Dask's superpower is coordinating vast amounts of data, pandas, dataframes, and NumPy arrays across multiple cores, even when the data is larger than your computer's memory. It has 3 key layers: the scheduler, the conductor, and the low and high-level APIs, the sheet music. We'll dive into what those APIs do next, but remember, Dask is how you scale from your laptop to a cluster with thousands of cores. Let's look at Dask's sheet music. The high-level APIs are your easy button. They provide user-friendly interfaces to parallelize common tasks in ML workflows, abstracting away the complexity. They are perfect for typical data transformations. The low-level APIs are for the advanced user. They give you ultimate control to create highly customized execution graphs. If you have a unique or complex task, the low-level APIs let you fine-tune exactly how the parallelization happens. This slide explains how Dask handles big data without hogging your memory. Instead of trying to read a massive dataset all at once, Dask cleverly breaks down every operation into sequences on smaller partitions of your data. It only reads each partition as it's needed. This is an incredibly efficient way to compute intermediate results, and is key to why Dask can handle datasets larger than the RAM on your machine. As always, the best way to master these concepts is through practice. This slide provides essential self-reading resources. The links to the Colab notebook, the Joblib distributed backend example, and the Dask/Scikit-learn post are excellent starting points. I highly recommend checking out the Dask distributed example. It shows how to prototype a solution on your local machine that's ready to be scaled up to a huge distributed cluster with just a single change. That brings us to the end of our lecture on parallel and distributed tasks. We've unlocked the power of multi-core processing to speed up our deep learning and machine learning models. If you can take away one thing, it is this: use the right tool, Joblib or Dask, for the right job to maximize your efficiency. Thank you for your time, and I look forward to seeing you in our next session